Google DeepMind may have just uncovered the first real clue to one of the most famous problems in math, a mystery that has puzzled mathematicians and physicists for nearly 200 years. These equations have shaped our world, and leaving them unresolved limits what we can predict. These equations are the reason we can model the weather, design airplanes, predict ocean currents, and understand how blood flows through our veins. They rest on the most fundamental laws of classical physics, conservation of mass, and Newton's second law. The Navier-Stokes equations are the foundation of how we understand fluid motion. The physics works, but hidden in the math is a question no one has ever been able to answer. Does a solution always exist? It sounds deceptively simple. But since the equations were first written down in 1822, no one has been able to prove it, or even disprove it. This single question has become one of the great unsolved problems in modern math, which is why it was named as one of the Clay Millennium Prize Problems in 2000, with a reward of $1 million to anyone who can solve it. And the prize is still unclaimed 25 years later. This is a problem so complex that it may be unsolvable with the math we have now. That's because the problem sits at the edge of what current math can express. To solve it might require new tools, new language, a new way of describing what happens when smooth, predictable flow blows up into turbulence and chaos. And that's what makes DeepMind's new results so compelling. The research team used a hybrid approach, blending high-precision mathematics with advanced machine learning to uncover something that, until now, existed only as theory. And, if they're right, this may be the first real crack in a problem that has stood for almost 2 centuries. A problem that bridges the boundary between order and chaos. In this video, we're going to look at what the team discovered, the breakthrough methods behind it, and why this matters for the million-dollar question. Does a smooth solution to the Navier-Stokes equation exist in 3 dimensions? So what are the Navier-Stokes equations exactly? In 1822, Navier published a set of equations to describe how fluids move through space and time. A few years later, Stokes expanded and formalized this work. Their combined contributions became what we now call the Navier-Stokes equations. These equations rest on 2 physical principles. The first is conservation of mass, which states that matter cannot be created or destroyed. As a fluid flows, the amount that enters a region must equal the amount that leaves, adjusted only by any sources or sinks. The second is Newton's second law of motion, F equals ma, which relates the acceleration of a fluid to the forces acting on it, such as pressure gradients, gravity, and viscous forces. Together, these 2 ideas form the basis for almost every calculation involving fluid motion. This broad range is what made them a foundation for fluid mechanics and modern engineering. Their flexibility, however, also introduces complexity. The results of these equations depend on the geometry of the domain, the shape of the boundaries, and the initial conditions of the flow. A slight change in any of these conditions can produce an entirely different outcome. Over time, researchers found that certain conditions lead to behavior that becomes increasingly difficult to control mathematically. These are the places where the solutions can start to behave irregularly, even when the physical flow itself remains smooth. And this is where we get a glimpse of how it is that these equations remained unsolved, even when we're able to use them in everyday applications. One of the clearest ways to see how this happens comes from a simple example: water flowing around a sharp corner. Imagine a stream of water flowing inside a channel and turning at a corner, a right angle. Along almost the entire path, the Navier-Stokes equations describe the flow accurately. The predicted velocities from the equations match what we can observe and measure in reality. The water flows smoothly around the corner, and the math and physics match. But at the exact point of the corner, the picture changes. The equations stop producing a finite value for velocity. Mathematically, the solution spikes to infinity. In reality, however, the water doesn't behave that way. It slows slightly, spreads out, and keeps flowing. Physically, everything is stable. But mathematically, the solution has broken down at this one point. This creates a paradox. The equations are precise and reliable everywhere except a single point, where they fail to give a realistic answer that matches what we observe. The physical system remains regular, but the math that describes it does not. The flow itself continues, but the proof of that behavior is incomplete. Viscosity is often invoked to explain why the real fluid stays well behaved. The viscous force should smooth out the sharp spike in velocity at very small scales. But adding viscosity does not automatically fix the singularity in the math. The equations themselves contain terms to describe this viscous force. So the equations still lack a well-defined, smooth solution at that one single point. And this isn't an isolated case. Similar behavior appears in other common flows. In Stokes' flow past a sharp edge, the stress field can diverge, even though the physical flow remains stable. In boundary layer separation, the equations can predict extreme gradients that are difficult to handle analytically, while the real flow would develop complex but finite structures. In high Reynolds number wakes, energy and vorticity can concentrate in very small regions, creating near singular behavior in the equations, even though the physical systems never actually reach those infinite values. All of these examples point to the same underlying issue. The physical world stays smooth, but the math we use to describe it blows up into unrealistic infinite values for velocity or pressure. The equations model most of the flow correctly, but fail at a few critical points where behavior becomes too sharp to capture with our current model. These examples show how the equations can fail at specific points, but these failures don't fully answer the Millennium Prize question. The problem proposed by the Clay Institute isn't about conditions with corners or edges. It asks whether these singularities can form on their own in smooth flows with no sharp boundaries. So let's look more into what exactly would constitute a proof for this million-dollar question. In 2000, the Clay Mathematics Institute listed the Navier-Stokes equations as one of the 7 Millennium Prize problems. Each problem carries a $1 million reward for solving, but the real weight of this question is not the money. It's that after more than 2 centuries, no one has been able to give a definitive mathematical answer to one of the most fundamental questions in fluid mechanics. The problem is posed for 3-dimensional incompressible fluids, fluids that don't change their volume when they move, in 2 kinds of spaces. The first is ordinary 3-dimensional space, called Euclidean space, R3. You can think of this as infinite space in every direction. The second space is periodic, R3 over Z3. This is like a looping world. If the fluid flows out one side, it reappears on the other side. This removes walls or boundaries and lets us focus on what the equations do on their own without interference from any edges or obstacles. The equations are considered with smooth, divergence-free initial conditions. Initial conditions just means how the fluid starts, its shape and velocity at time 0. Smooth means that the motion is well behaved. No spikes, no infinite values, no abrupt changes. And divergence-free means that the fluid doesn't compress or expand. What flows in must flow out, like water in a closed pipe. For simplicity, there's no external force. Everything that happens must come from the fluid's own internal dynamics. The core question, then, is simple. Starting from a smooth, finite energy initial state, does the fluid remain smooth for all time? Or can a singularity, a point where the velocity becomes infinite, appear in finite time? A singularity here doesn't mean a physical explosion. It means the math itself breaks down. The equations no longer give a valid answer at a specific point. So the question is whether the equations themselves can create a singularity spontaneously out of a fluid's own internal evolution. The official problem statement gives 4 ways this mystery could be resolved. Proving any one of these would solve the problem. One option is to prove existence and smoothness on R3. Prove that for any smooth, incompressible flow with finite energy and no external forces, the solution remains smooth for all time in finite 3D Euclidean space. Option 2 is to prove the existence and smoothness on R3 over Z3. So to prove the same thing in the looping periodic space, showing the equations never blow up even without boundaries. Option 3 is to show the breakdown on R3. This would require giving an explicit example of a smooth incompressible initial data that then leads to a finite time singularity, showing that the equations can break down in infinite Euclidean space. And part 4 is to prove the breakdown in periodic space, show how the singularity can also form in the periodic looping space. In short, either fluid motion remains smooth forever, no matter how long you let it run, or there exists a special flow where the equations self-destruct, forming a singularity in finite time. Proving smoothness, or finding even a single counterexample, would settle one of the deepest open questions in mathematics, and unlock a Clay Millennium Prize problem worth $1 million. The corner singularity that I previously explained doesn't fall into this definition, because that situation is caused by geometry, not by the evolution of the equations themselves. If the boundary is smoothed, the singularity vanishes. The Clay problem strips away those external complications. It asks whether the Navier-Stokes equations alone, starting from a smooth, well-behaved state, can generate a singularity in finite time. And that's the core of why this problem remains unsolved. The equations work in practice, they match physical flows, and they model reality to extraordinary precision. But right now, no one has been able to prove whether smooth solutions exist forever in 3D space, or whether they can blow up from within. In the formal problem statement written by Charles Pfefferman, he writes, "Let me end with a few words about the significance of the problems posed here. Fluids are important and hard to understand. There are many fascinating problems and conjectures about the behavior of solutions of the Euler and Navier-Stokes equations. Since we don't even know whether these solutions exist, our understanding is at a very primitive level. Standard methods from partial differential equations appear inadequate to settle the problem. Instead, we probably need some deep new ideas." But why should we care if the math breaks down? What does that actually mean for the real world? If the equations break down in 3D space, the consequences would ripple out into how we understand and predict the physical world. A singularity in the Navier-Stokes equations would mean that there are moments when smooth, well-behaved flow can collapse in finite time, creating a point where the math can no longer predict what happens next. The equations, which are used in everything from climate models to aircraft design, would contain a built-in limit to their ability for predictions. Take weather forecasting. At large scales, turbulence is modeled, not perfectly understood. If singularities are real, they could represent hard limits on how far ahead a forecast can ever be trusted. Not because of missing data or better computers, but because the equations themselves stop giving physically reasonable answers beyond a certain point. Or consider the design of an aircraft wing. Engineers rely on these equations to model how air flows around a surface under changing conditions. If a singularity can form in certain flows, then there are situations where no equation can guarantee what happens next, only approximations and statistical models. This is about a fundamental boundary between our ability to predict what happens based on a starting scenario and chaos. If a blowup is possible, then perhaps no amount of computing power can predict the future past a singularity. But if smoothness can be proved, the opposite would be true. The equations would guarantee that, at least in theory, fluid behavior is predictable forever. This is why the Clay problem matters so much. It's both a math question and a question about our ability to make predictions about the physical world. So if the stakes are this high, why hasn't anyone been able to crack the problem after 200 years? And if you want to keep up with these kinds of deep dives, don't forget to subscribe. And if you're enjoying this video, give it a like. Your support really helps me continue the work of this channel. Mathematicians have been trying to understand the Navier-Stokes equations for more than a century. Many of the ideas that form the backbone of modern fluid dynamics and mathematical analysis grew out of attempts to answer the same question we still face today. Can smooth flow stay smooth forever, or can it break down in finite time? The core difficulty begins with nonlinearity. One of the central terms in the Navier-Stokes equation describes how a moving fluid carries its own momentum. A small perturbation in one region of the flow can propagate and can influence every other region. This makes the system sensitive to its own past, and that sensitivity can grow. And this is where turbulence emerges. A smooth flow can develop complex structures that fold, twist, and spiral. Energy moves through these structures and cascades to smaller and smaller scales. Physically, this gives us everything from vortices in a river to the chaotic motion of the atmospheric storms. If the energy concentrates too strongly in a small region, the velocity could diverge and a singularity could form. To prove smoothness would mean showing that no matter how fine the structures become, that cascade never reaches the point of blowup, or reaches an infinite velocity or pressure. To prove blowup would mean constructing a specific example where it does. This is the barrier that has stood for 2 centuries, but over time there have been important advancements that have been bringing us closer and closer to the answer. The first major progress came from John Leray in 1934. Leray introduced the idea of weak solutions, which satisfy the equations in an average sense, rather than point by point. He proved that these weak solutions exist for all time, a major step forward. But he couldn't prove whether they remain smooth or develop singularities. That gap between existence and regularity remains a crucial challenge of the Clay problem. Later, Olga Ladezhinskaya and others refined the theory for two-dimensional flows, where the equations behave better. In 2 dimensions, global smoothness can be proved. In 3 dimensions, though, the same techniques hit a wall. The turbulence and instability of 3D flows introduce complexities that don't appear in 2 dimensions. To understand why this question has resisted every tool so far, we need to look a little deeper at the heart of what makes fluid motion so unpredictable: turbulence. Turbulence is so complex that even describing it rigorously has challenged science for more than a century. In 1883, in a now famous experiment, Osborne Reynolds injected a thin line of dye into a flow of water through a glass pipe. At low speeds, the dye formed a smooth laminar stream. But past a critical threshold, the line broke apart into swirling, chaotic structures. Turbulence. From this, he derived what became known as the Reynolds number, a dimensionless measure that predicts when a smooth flow transitions to turbulent flow. It was a simple experiment, but it captured the core of the problem. Turbulence emerges suddenly, and once it does, fluid behavior is extremely complex. By the early 20th century, turbulence was already seen as one of the great frontiers of classical physics. Even Heisenberg, after helping to reshape quantum mechanics, famously is supposed to have said, "When I meet God, I'm going to ask him 2 questions. Why relativity and why turbulence? And I'm pretty sure he'll have the answer to the first." This sentiment captures the frustration many physicists have with turbulence, a phenomenon that's so common in everyday life, but seemingly impossible to describe with equations. For decades, physicists developed empirical laws to describe turbulent flows, scaling laws, statistical averages, and different types of models. In the 1940s, Andrei Kolmogorov proposed his celebrated Kolmogorov theory of turbulence, describing how energy cascades from large to small scales in a self-similar way. But even this elegant theory sidesteps a fundamental question on what happens at the smallest scales. And can the equations themselves even hold together there? This is where physics and math diverge. Physicists can describe turbulence statistically. Mathematicians need to prove whether the Navier-Stokes remain well-behaved or collapse at those small scales. And so, as physicists measure and model turbulence, mathematicians search for proof and understanding. Terence Tao has spent years studying the problem. He's explored the possibility of using techniques from harmonic analysis and dispersive partial differential equation theory to make progress. But even with modern numerical simulations, the problem resists resolution. A simulation can approximate flow behavior at high resolution, but if a singularity exists, it may occur at scales far below what can be computed. So simulations that are not precise enough can't offer definitive proof. However, now, something entirely new has entered the field, a tool to search through the hidden structure of the equations and hopefully see new patterns. So, what happens when a new tool starts searching the landscape of these fluid equations? In 2025, Google DeepMind and a team of collaborators used advanced machine learning methods to probe the equations directly to search the mathematical space for structures that are nearly impossible to detect through analysis alone. One of the key figures behind this breakthrough is Javier Gómez-Serrano, a mathematician whose work has been central to modern singularity research. Gómez-Serrano has spent years developing new techniques to rigorously study fluid equations and to construct singularities in related systems. His earlier work laid much of the mathematical groundwork that made this computational search possible, especially in how to rigorously validate delicate structures that emerge at very small scales. In this project, he and collaborators combined that mathematical expertise with DeepMind's machine learning systems to search systematically for previously hidden singularities. More on what that means later. Their approach blends 2 worlds, precise numerical computation and machine learning. They built high-resolution solvers capable of tracking flows with near double precision accuracy, then trained algorithms to look for patterns that might reveal how singularities could form. The key idea is simple but powerful. If singularities exist, they might be unstable, appearing only in extremely delicate configurations that collapse if perturbed. These are precisely the kinds of patterns that are difficult for human intuition to find, but well-suited to systematic computational search. Instead of starting with the full Navier-Stokes equation, the team is first focused on simplified but closely related fluid systems, settings where the same mechanisms that govern Navier-Stokes appear in a more controlled form. Using these systems as a testing ground, they began to uncover solutions that exhibit unstable behavior. The mathematical analysis of such singularities is incredibly delicate. For decades, researchers have looked for either a proof of smoothness or a construction of blowup, but both paths require finding the right structure in an infinite space of possibilities. The DeepMind system is designed to explore that space at scales that human calculation cannot easily reach. They combined ideas from physics-informed neural networks, optimization, and high-precision partial differential equation solvers to do this. The machine learning component does not solve the problem, it identifies candidate solutions, which can then be checked rigorously with mathematical tools. This is not a replacement for a proof, but it can reveal places where a proof might begin. One of the most significant findings is the discovery of unstable singularity candidates in fluid systems that are structurally similar to the Navier-Stokes. These singularities have been nearly impossible to isolate in the past. The computational search was able to find and characterize them with enough precision that mathematicians can now study their structure directly. If these singularities hold up under further scrutiny, they offer a potential path to one of the two solutions to the Clay problem, proving finite time blowup. If they don't, their absence can guide mathematicians towards the conditions that might guarantee smoothness. For the first time, we may have a concrete target, and this is where the story shifts from theory to discovery in the mathematical landscape. But before we look at what DeepMind found, we have to understand where they went looking, and why it wasn't the actual Navier-Stokes equations themselves. To understand why DeepMind's search for singularities matters, it helps to look closely at a related problem, one that has haunted mathematics even longer than the Navier-Stokes problem. If you remove viscosity from the Navier-Stokes equations, you arrive at the Euler equations, formulated in 1757. These equations describe the motion of an ideal fluid, one with no friction, no energy loss, and no damping. They're simpler to write down, but far more difficult to control. Mathematicians widely believe that if singularities exist for Euler, they may appear more readily than for the Navier-Stokes equations. Viscosity acts like a stabilizing force, smoothing out the flow at small scales. So removing this force, there's nothing to keep small-scale instabilities from blowing up to infinity. If blowup can occur in the idealized conditions, that may point the way to understanding blowup in viscous flows too. And if smoothness can be proved here, it would represent an equally profound breakthrough and a point to smoothness in viscous flow. The search for singularities in Euler's equations has a long history. Decades of work have revealed complex structures and how energy can concentrate, how vorticity can stretch and fold, and how instabilities may grow. But no proof of finite time blowup has ever been found. This is where DeepMind's search becomes more interesting. By looking for unstable singularities in equations like the Boussinesq equations, which bridge the gap between Euler and Navier-Stokes, they're effectively probing the terrain where the singularities are most likely to appear. And so, rather than tackling the Navier-Stokes head-on, they went into related and slightly idealized cases where singularities might be easier to spot. These related equations of fluid dynamics are more idealized, but retain the same nonlinear structure that drives fluid blowup. The DeepMind research team focused on three canonical systems. 1. CCF. This is a one-dimensional model that captures essential blowup dynamics in a stripped-down setting. This equation is often used as a testbed because its structure mimics the cascade that can appear in higher dimensional fluids, but is simpler to solve. Second is the incompressible porous media equation, IPM. This is a model describing fluid flow through porous media, governed by Darcy's law. IPM retains many of the mathematical difficulties of Navier-Stokes, including the possibility of finite time singularities, but in a simpler geometric context. And 3 is the Boussinesq equations. These are equations that describe buoyancy-driven flows, often used in modeling atmospheric and ocean dynamics. Under certain symmetry conditions, the 2D Boussinesq system is closely related to the 3D Euler equations, which in turn are closely tied to the Navier-Stokes problem. The goal of studying these equations was to look at self-similar solutions, flows that shrink or stretch in a predictable way as they approach blowup. These are exactly the kind of solutions many mathematicians believe would exist if a singularity can form. The researchers used physics-informed neural networks combined with Gauss-Newton optimization to search for solutions with vanishingly small residual errors, with a level of accuracy constrained only by the inherent round-off errors of the GPU hardware. They reach near double precision limits, which meets the stringent requirements for rigorous mathematical validation by computer-assisted proofs. So what is a singularity? A singularity is a point where the equations stop working, where the velocity predicted by the model becomes infinite. But not all singularities behave the same way. A stable singularity is robust. Even if you slightly change the starting conditions, the solution still collapses in the same way. It's like a ball rolling into a bowl. A small nudge in one direction doesn't stop it from settling at the bottom. However, an unstable singularity is fragile. If you alter the starting conditions even slightly, the solution veers away and the singularity disappears. This is like balancing a pencil on its tip. Technically possible, but easily lost with the smallest disturbance. This distinction matters because if singularities exist for Navier-Stokes equations, they're expected to be unstable. That's why no one has been able to find them analytically. And that's exactly where DeepMind's computational method succeeded. They were able to systematically search and uncover candidate unstable singularities with unprecedented precision. So let's get into what they actually found. For each system, they discovered families of solutions. For IPM, they identified stable and 3 unstable singularities. For Boussinesq, they confirmed a stable singularity and found at least 3 unstable ones, plus a candidate 4th. And for CCF, they achieved near machine precision results on both unstable and stable singularities. These unstable singularities are mathematically delicate. If you change the initial conditions even slightly, the solution veers away from the blow-up trajectory. This is why they're so hard to find analytically, and why computational search can succeed where analysis alone has struggled. To make sense of these solutions, the team performed a linear stability analysis. For the nth unstable singularity, they found exactly n unstable modes, directions in which the flow can diverge. This structure gives them an empirical hierarchy of singularities, showing how complexity builds up as n grows. This isn't a proof of singularity for the Navier-Stokes itself, but it's the first time anyone has systematically mapped out a landscape of unstable singularities in a system so closely tied to it. And that matters because if a singularity exists for Navier-Stokes, it may look a lot like these. For the first time, we have a new way of discovering singularities in systems of fluid equations. So the next question is, what happens when this method is applied to the full Navier-Stokes equations? If these singularities are real, what would that mean for one of the hardest problems in math? For the first time, researchers have identified explicit families of unstable singularities in systems that directly mirror the structure of the Navier-Stokes. That matters because these singularities are the kind of mathematical objects many experts believe must exist if blow-up is possible. They're fragile solutions requiring perfect alignment of initial conditions, and that's exactly what one might expect of a Navier-Stokes singularity, if one exists at all. So this discovery gives mathematicians something they've never had before, a map of what a candidate singularity could look like. It doesn't prove finite time blowup for Navier-Stokes, but it narrows the search. It shows that the underlying equations are capable of supporting structures that resemble what blowup would require, at least in closely related systems. And if a singularity like this can be rigorously constructed or ruled out in the full Navier-Stokes system, that would settle one of the greatest open problems in modern math. If such a singularity exists, it would mean there are limits to prediction built into the equations that govern our world. Fluid motion would contain places where smooth flow can collapse into something no longer predictable. But if no unstable singularity exists and smoothness can be proved for all time, it would be a great triumph in mathematical analysis and a statement about the fundamental stability of fluids. Either way, the path to that answer now looks different than anyone imagined 200 years ago. Instead of searching through infinite possibilities, mathematicians now have candidate structures to probe, analyze, and rigorously use to prove or disprove the statement. DeepMind's work has brought us closer to answering questions about these fundamental equations and the way we can approach mathematical challenges. But understanding what these singularities mean and whether they truly exist in Navier-Stokes itself is a different kind of challenge. The discovery of unstable singularities is a major development, but it isn't a proof. It's a method, and it's a method that has attracted doubt and concern. The authors write at the end of the paper, Given that there's a recent concern about over-optimism in using physics-informed neural networks as general-purpose partial differential equation solvers, we stress that the neural networks are not used for this purpose in this work. Rather, the goal is to discover solutions to differential equations that have not been found before. Here, the physics-informed neural networks are utilized to parameterize the particular solution of the equations we wish to discover. And the pipelines for training the models are designed and constructed with the intention of making the network satisfy all the math assumptions and constraints imposed by the problem at hand. Machine learning can search through spaces far beyond what humans can compute, but it doesn't offer mathematical certainty. Every candidate singularity is still a numerical structure, sensitive to resolution, algorithmic choices, and the way equations are approximated. This is what makes the problem so challenging. Singularities, if they exist, live at vanishingly small scales where traditional numerical methods begin to fail. The closer you get to a blow-up, the more unstable the simulation itself becomes. Even a tiny numerical artifact can create something that looks like a singularity, but isn't. And this has happened before. In other fields, numerical discoveries have hinted at structure long before proofs caught up, and sometimes those hints were wrong. Singularities may appear in computation and vanish under rigorous analysis, or they may turn out to be real, but only in a form more subtle than the machine can see. And if these singularities are unstable, as the results suggest, they may be especially prone to disappearing when examined too closely. This is why the Clay problem still belongs to math. AI can illuminate the terrain, but only a proof or a counterexample can resolve the main question. So why ask for proof? As the Clay Institute put it, a proof gives not only certitude, but also understanding. And all of this to say that real work still lies ahead. Now that we've seen a glimpse of what might be hiding inside these equations, the question is, how do we prove it? The discovery of unstable singularities in related systems doesn't prove or disprove the Clay Millennium Prize Problem. But it gives mathematicians something they've never had before, a concrete set of targets. The next steps are clear, but far from easy. One path is to take these candidate singularities identified in systems like Boolean-esque equations and incompressible porous media, and push them closer to the full Navier-Stokes equation. This involves proving that similar structures can either exist or be ruled out in the full three-dimensional flow. To make that leap, mathematicians will need to develop new analytical tools that can track how energy concentrates at very small scales. Standard energy bounds are too coarse. What's needed are sharper estimates that can either control or capture the blow-up mechanisms these singularities suggest. Another path involves rigorous computer-assisted proofs. High-precision simulations combined with mathematical verification methods may be able to either confirm the existence of singularities or demonstrate constraints that prevent them. This type of hybrid analytical computational proof has already begun to shape other fields like dynamical systems and number theory. For Navier-Stokes, it could be a turning point given that we now have a landscape of what the unstable singularities can look like. And then there's the possibility of constructing a minimal blow-up scenario. If mathematicians can rigorously build a solution that behaves like these singularities, it could settle the problem in one direction. If they can prove such a scenario can never occur, it would settle it in the other. This is what makes DeepMind's results so important. They don't provide the answer, but they make the question more concrete. The infinite space of possibilities has narrowed to a specific structure, something to analyze, to prove, or to disprove. But this is far more than a technical puzzle. It's a moment that raises bigger questions about how we make new math and science discoveries. The Navier-Stokes equations are among the most widely used tools in science and engineering. We trust them to predict how air moves across the planet, how the ocean circulates, and how storms form. Yet, the mathematics behind them still contains a gap no one has been able to close. If singularities can emerge spontaneously, there may be moments where no amount of computational power can give a reliable forecast, because the equations themselves contain points where they break. If smoothness can be proved, then the opposite is true. The equations guarantee stability, and our predictive power rests on a firmer foundation. The role of Google DeepMind here is changing how we explore mathematical landscapes. AI can search spaces that human intuition struggles to map. It can expose patterns, instabilities, and structures that may take years to find by hand. Proof, however, currently remains a human task. Whether this work ends in a proof of smoothness or in the discovery of a singularity, one thing is clear. We're closer than we've ever been to understanding one of the most basic questions one can ask about fluid flow. Do unique solutions always exist? For centuries, progress in math has come from insight, from a single idea that unlocks a structure no one could see before. But this may be one of the first great problems where that first glimpse came not from a person, but from an AI approach. That shift matters, because Navier-Stokes isn't the only frontier. There are 6 other Clay Millennium Prize Problems, each one a wall that has resisted some of the best minds of the modern era. All of these may, in time, face the same kind of AI-augmented exploration that Google DeepMind is leading for this problem. If these unstable singularities turn out to be real, they'll mark not just a mathematical milestone, but the moment where AI became part of the process of mathematical discovery itself. And even if they're not, even if this particular map turns out to be a dead end, the tools have changed. The frontier will not be explored in the same way again. The authors note, "We hope our results would encourage new numerical designs and discovery methods to develop for similar applications across the computational community. Our results highlight the importance of combining domain-specific mathematical insights with modern computational tools to tackle problems that have resisted purely analytical or purely numerical methods." And while Google DeepMind is pushing the boundaries of fluid dynamics, they're also competing with a new wave of AI systems. One of them, DeepSeek R1, has shaken the world with its high performance, low cost, and a design that's rewriting how models learn to reason. Check out my recent video on the secrets of DeepSeek to learn more about the aha moment that's redefining the future of AI.